I could give you 10 marbles and some string, and you could put one marble next to, right? Do it in a chain. That's not that complex. Someone else, I could give the 10 marbles and they may connect every marble to every other 9 marbles. You get a very weird looking, very complex structure. So it's the interconnection. So what we discovered was this revolution is that it's not the number of genes who make a human being complex in a worm. It's the fact that the genes give rise to, basic biology proteins. So the genes and the protein products interconnect in much more deeper ways in a human being than in a worm. And these interconnections were known as molecular pathways. So what the realization occurs in 2003 is, wow, it's not mapping the genes. We got to map these molecular pathways, these mechanisms. And in fact, genes create proteins. Proteins can feed back on themselves and turn off genes. And this became a world called epigenetics, which said, oh, what you eat, where you're born, what you think can turn on and turn off genes. In fact, in some very interesting experiments, they showed that two twins with the same gene for a particular feature, under certain conditions, you can turn them off and turn them on. So this completely put biology on its head. So at that time in 2003, I was randomly walking back to MIT, and my old advisor said, Shiva, you got to come finish back your PhD. There's a new field called systems biology. You love computing. You created this. You created all sorts of technology systems. You could imagine if we could take the entire cell and if we could mathematically model all the molecular reactions in the cell. If we could do that, then instead of killing animals all day, clinical, preclinical work, we could use a computer to mechanistically model all these chemical reactions and test compounds. How would that be? To me, that was, and this was seen as a grand challenge the NSF had put forward, David, in 2003. So I found someone else to run EchoMail, which was the email analysis company, came back to MIT at the age of 40, and I had to take all my grad courses again. It was quite interesting, right? I had to take my biology courses, pass what are called qualifying exams. And by the way, those people don't know, in order to get a PhD at MIT, you have to get in front of professors. They give you 4 oral exams, on different topics, and then 4 written exams, and you get grilled. 50% of the people don't make it through those PhD exams, and then you have to write it. It's really a sort of a Navy SEAL type program. So I came back, had to do all those things, and you have to write a thesis in an area that's new. So I ended up, my thesis was to create a technology called Cyto, which meant cell solve. And Cytosolve was a complete technology platform I built. If email was the electronic digital version of the interoffice mail system, Cytosolve was a way that you could capture the molecular system in silico on the computer. And so it wasn't an AI approach. It was in many ways much more better than AI, because AI guys just take an input and output and they want to fit a line to a curve, to put it simply. AI is good for certain problems, but it sucks at mechanistic understanding. So I ended up building Cytosolve 2007. And again, I created a technology that could, so if you take cancer, I could take every paper in cancer, extract out the reactions that each one of those papers are talking about, interconnect them, mathematically convert them, and compute it. So after I finished that, I applied for a Fulbright because I said, okay, now I got my MIT degrees. Now, if I studied alternative medicine, people can just trash me. Probably trash me anyway, but it'd be harder, right? So I applied for a Fulbright to say, could I figure out the scientific basis of how my grandmother did these traditional systems of medicine? I was fortunate to get it. In fact, the front page of MIT featured me. It was a front page article that said, Dr. Shiva, armed with 4 degrees, wants to go back to India to study traditional medicine. They didn't understand why I wanted to do that. Why wouldn't I just want to start my next company? So I went back to India and I traveled all over India, and I had been studying these systems anyway. And what ended up happening, David, I found out that the ancient systems of Indian medicine used a terminology, a lingua franca, to describe the body, which we in the West would say that sounds like bullshit, right? Sounds like some, snake oil. What I found was those terminology matched 1-to-1. It was sort of a Rubik's Cube I solved, like the Rosetta Stone, matched 1-to-1 with the 9 principles that you learn in engineering systems theory. It's called control systems. So these ancient rishis of India were really not medical guys. They had realized that the body was a complex system and you needed a different language. So when my grandmother used the words vata, pitta, kapha, these 3 terms to describe your body's constitution, it matched interestingly to, in general systems theory, to call transport, conversion, storage. Anyway, I discovered that, wrote an important paper on that. And in fact, when I was leaving India on my Fulbright, side note, it's a whole story we could do on this, I won an award in India and got appointed by the Prime Minister of India to run the largest scientific institution. They said, why are you going back to India? Why don't you help your homeland? And that's when I discovered that the entire science institution of India, which was filled with amazing people, was suffocated by the 1940, pre-1947 system of feudalism. This is why no Indian scientist post-independence has won a Nobel Prize in India. They all have to come to America because of and so I was given a huge home in India running, 4,000 people, and I couldn't stand what I saw. I wrote a white paper exposing this. I was fired, terminated under death threats. I had to leave India, come back to the United States. It's a fascinating story because you thought this would be embraced. Anyway, when I came back in 2009, I started a course at MIT called Traditional Medicines and Systems Biology. We'd have, 200 people show up to that course. MDs on one side of the room, hardcore engineering guys, and the other side of the room where you would call these woo-woo people, yoga people, etc. But in about an hour to 2 hours, I was able to intersect these two worlds with this deep understanding of engineering systems principles. That became a thing called systems health. So anyway, Cytosolve, after I came back, my advisor and I, we said, hey, let's start a company. We thought pharma guys were basically killing people in side effects. The way pharmaceuticals work, it takes 13 years to build a pharmaceutical drug. Why is that? They follow a medieval approach, David. They find a synthetic compound that they create. And maybe this is how it works. You put in a cell, in a test tube, you put cancer cells, for example, and you drop a bunch of synthetic compounds. You go, wow, that looks like it's killing it. Then you apply for a patent, and then you go and get $40-50 million in funding, and you open up a lab and you start testing this compound in a test tube. That's called in vitro testing. That may take 2 to 3 years. If you make it after that, you raise more money and you go kill a bunch of animals, another 3 years. If you find out that you don't kill enough, you're not killing too many animals, 6-7 years, you file to the FDA to say, I want to test my compound on humans. They give you what's called an investigational new drug filing. It's called an IND. And that may take 2 years to get that allowance. And then you go test on small groups of humans, phase 1. If it makes it out of that, phase 2, phase 3. This process takes $5 billion, 13 years. And what's been happening, David, and most of the people at MIT and real scientists know this, over the last 30 years, pharmaceutical companies have been tanking because this is a medieval process. And the way they're actually doing, they're basically throwing shit against the wall. And then if something works, then they say, oh, I know why it works. It's called rationalized drug development. So my theory was, and by the way, the drugs that come out, they only work for 10% of the people. And this is documented. Most of the other people have the side effects. That's why when you watch those commercials, they have to say, well, this could happen, that could happen.
And then you get 30 seconds of disclaimers as to potential side effects.
Exactly. Right. So I thought Cytosolve would be revolutionary because we could figure out all the shit that's not going to work ahead of time. And in fact, what happened was after I published my thesis, there was a very important, by the way, in the world of science, the #1 journal in science, it's like the Academy Awards. If you get published in Nature, you're like a star. Okay. And very few professors ever get published in Nature. Anyway, there's an article that came out in Nature saying if you're going to solve cancer, we shouldn't just be using one compound. We should be using cocktails. There's only one 4-drug cocktail that the FDA has allowed that was for quote unquote AIDS. Okay. And this paper written by the 4 leading guys in the world in cancer therapy cited my thesis as the only technology framework that could do this. So when that paper came out, we raised about $1 million in 2 weeks. And we said, why don't we use our technology to look at every generic cancer drug, mathematically model pancreatic cancer, which is a very horrible cancer. And could we discover something on the computer, a 2-drug combination? We just did this as a proof of concept to show the power of the platform I created. And in 11 months, lo and behold, we not only discovered, after looking at trillions of combinations, a 2-drug combination better than the gold standard called gemcitabine. We applied for an investigational new drug filing, and we got it allowed by the FDA. In fact, one of the senior people at the FDA called me and they said, we don't normally do outbound calls, but we were so impressed by what you've done. It's the future of 23rd century medicine. They gave us our allowance, and we didn't even know we'd get that far. And then we went to a cancer center called MD Anderson, and we created a relationship with them to continue to advance this. But the bottom line is Cytosolve was this very powerful way we could obviate the need for animal testing. But pharma moves way too slow, and they really don't want to solve the problem. They're like a dinosaur, which is making trillions doing the old way. And if you look at Pfizer's revenue in 2012, they did $65 billion in revenue. Their revenue in 2020 was, guess what, $45 billion. They've been losing money because of this old system. The reason they've been surviving is on old patents, like Lipitor patents. And as those drugs come off patent, in fact, year over year now, pharma spends more and more money on R&D, and less drugs were even being allowed by the FDA because of the toxicity. So pharma by 2020 realized, shit, we have a major problem. That's why the vaccines were so important, because you had Operation Warp Speed.
Well, that's what I was going to say, because you're saying it took too long to do the R&D. You have to go through in vitro, then animal testing, then human testing. And it seems that in recent times, we've gone from taking too long to taking warp speed and moving at the speed of science, which might mean too fast before any of these tests have ever, been done properly.